You see, the Webb telescope can look so far out that it's catching light that has been voyaging for more than 13 billion years. Yet the universe has been growing, and thus the light has been extending. For the most distant worlds, we're thinking back in time nearly to the Big Bang. The fabric of existence channels you so that, as a matter of fact, you're possessing a smaller and smaller cone of space. You're getting expelled through the texture of space-time. Our ongoing perspective on the universe should be refreshed in light of this. The James Webb Space Telescope has found something that absolutely goes against the theory of the universe's origin, which is the standard Big Bang hypothesis that explains our beginnings. According to Neil deGrasse Tyson, the Webb telescope identified black holes from a past universe that were responsible for the creation of our own. The James Webb Space Telescope is disturbing the apple cart. All of a sudden, we understand that we might need to rebuild all the textbooks about the start of the universe. Is now the right time to modify our astronomical understanding? If this is the case, how significant will the corrections be? Join us as we explore the bewildering discoveries made by the JWST. Is it conceivable that the estimations were off or that they were inaccurate concerning the Big Bang? We will find newfound systems uncovered by JWST, figuring out the hot theory of how things came to be. This was one of the greatest scientific accomplishments of the last 100 years. The current universe, according to this theory, formed from a denser, hotter, and more uniform prior state. After being proposed as a possible alternative to the standard model of cosmic expansion, the hypothesis was wonderfully validated in the 1960s by the discovery of the cosmic microwave background, known today as the early-stage fireball. The Big Bang has been the driving explanation for almost 50 years regarding how the universe came to be. It relies on an inflationary period that happened before the Big Bang to set the stage. However, astronomers and astrophysicists have long presented constant problems with cosmic inflation and the Big Bang, and the JWST has added a new issue, extra complexity to the cosmic story. It might significantly change the way we comprehend the universe if it finds early galaxies that are far larger than expected. The discovery of these massive galaxies in the early universe by the JWST raises the likelihood that our current perspective on the universe needs reassessment. Current cosmic models disagree with this view. In its brief time in operation, the James Webb Space Telescope has already revealed previously concealed insights regarding the universe in the initial few 100 million years following the Big Bang. Everything is all worked up in light of the James Webb Space Telescope. It has become clear to us that we might need to revise every single textbook on the subject of how the universe formed. The arrangement of gigantic galaxies collaborating with stars has been a surprising revelation. Using the infrared detecting instruments of the JWST, researchers have identified 6 huge galaxies that were present throughout the early universe. If the size of these objects is confirmed, they could impact the way we contemplate where galaxies come from. These results depend on data obtained by the James Webb Space Telescope and published in Nature. The data show the universe as it was 13.5 billion years ago, or around 3% of its current age. If galaxies are so bewildering, then what exactly are they? These galaxies show signs of development equivalent to our own Milky Way, which is 13 billion years old, appearing only 500 to 700 million years after the massive blast that signaled the beginning of our universe. The celestial masses in these galactic bodies are a few billion times more prominent than our Sun, with one potential beast flaunting an incredible 100 billion times the mass of our Sun. Around 60 billion suns of stars are incorporated within our Milky Way. Clearly, these galaxies dwarf even our own Milky Way in size. Expressing her shock, co-author of the study and cosmologist Dr. Arne Nelson of the University of Colorado Boulder said that the unexpected appearance of such enormous objects is confusing. This is a gigantic revelation, and we believe that it's a colossal discovery. The most thrilling part of this exceptional instrument we've placed in space is finding things that we didn't expect, that we can't make sense of, because that means that we have to change how we understand the universe. During the early universe, galaxies with celestial masses comparable to the Milky Way formed quickly, which was not expected by conventional wisdom. This amazing finding runs counter to long-held cosmological beliefs that universe development is a slow process, beginning with tiny star and dust clusters. The story goes that stuff in the early universe formed gradually. However, the newfound enormous creatures aren't sufficiently explained by this narrative. Dr. Evo La, the head scientist, is curious about the apparent acceleration in the development of these massive galaxies. The universe didn't form overnight, according to popular assumption, and this revelation challenges that idea. Using a casual term, astronomers call these objects universe breakers, and they're fulfilling the moniker by affecting the way we think about the development of the universe. Although she was not directly involved in the research, English cosmologist Emma Chapman of the University of Nottingham argues that our understanding of the early universe may be fundamentally altered if these results hold up. The discovery of monstrous galaxies around the Big Bang projects doubt on the concept of a Dark Ages period and raises the likelihood that star formation was occurring earlier than previously accepted. A word of caution, however, from the researchers. Before we start changing the history of cosmology, one such hypothesis is that supermassive black holes could conceal some of these creatures. What looks like stars in the pictures could truly be dust and gas imploding under the power of gravity. The complexities of black hole formation and development during these early years remain a mystery, according to another researcher not involved with the work. She states that the new evidence does not cast doubt on cosmology but rather raises questions about how these objects formed, were framed, and how they extended to affirm their discoveries. Researchers might utilize spectroscopy to snap a photo of the distinguished objects. Spectra would uncover how old they are. The light transmitted by worlds in the early universe has been extended significantly on its way to Earth, as demonstrated by their enormous redshift. A higher redshift demonstrates that the light has been extended, which in turn demonstrates that the galaxy is older and farther away. Spectroscopy can uncover the age of these galaxies that have been assigned as high redshift competitors, or whether they are indeed galaxies that are inherently redshifted from a later cosmic period. Points of view from Michael Bond-Cullen indicate that, notwithstanding the way that extra perceptions are needed to validate the outcomes, space experts have hypothesized that the recognized mass means a stunning revelation. One way or another, even with a half reduction in the sample size, the known heavenly mass from this cosmic age could be multiple times more than whatever was previously thought. Nature Cosmology presents the capricious perspective of University of Texas at Austin professor Michael Bond-Cullen, who reveals insight into the matter. The most famous cosmological model, lambda CDM, which stands for cold dark matter, proposes that in the early universe, dark matter and standard matter were combined broadly. A small portion of the trapped standard matter changed into stars as the dark matter glows fell, bringing forth the first cosmic systems. As indicated by Bond-Cullen, the vast microwave background provides solid proof for the distribution of matter in the early universe. To find a place with the high-mass worlds found by the JWST, he set out to figure out what part of conventional matter ought to starburst. Star creation would have made use of essentially every particle in the universe. He concluded, however, that this practically perfect productivity is thought of as impractical by Bond-Cullen. Conversely, he claims that the ongoing universe works at a proficiency of generally 10%. Although he didn't partake in the research, MIT's Mark Vogelsberger applauded the paper's hypothetical approach. According to Vogelsberger, the strength of the gauge is inferred from not very many suppositions. Is lambda CDM tossed out of the running, not enduring Bond-Cullen's computations? He avoids totally discounting lambda CDM, expressing that no other hypothesis comes close to matching its capacities, leaving the probability of supplanting it as a last resort. But are there some other conceivable reasons at work here? Mysterious discoveries. An intriguing early world found only 500 million years after the Big Bang was uncovered by Haley Williams, who led a group from the University of Minnesota. The low appearance of the universe is also subject to gravitational lensing enhancement, which is seen with the JWST, compared to worlds from a bit later period. Its star creation rate is multiple times higher, as Williams points out. Although this universe is less in mass than the ones concentrated on by Bond-Cullen, Williams makes a reasonable deduction on whether this extreme star development might be applied to galaxies with larger masses that are at the equivalent redshift. In any case, Bond-Cullen continues to exercise caution due to the article's humble size. It is just 105 light-years across, which is much smaller than the typical galaxy. He considers the possibility that it could really be a globular cluster. Lambda CDM changes are one potential answer to the cosmological model strain. Early dark energy proposes changing the conduct of dark energy soon after the Big Bang. This adjustment has the potential to bring the Hubble constant-related conflicts into congruity with other perceptions. As indicated by these hypotheses, the early universe had more matter than it actually has. For this case, according to Bond-Culin's estimations, early galaxy matter densities would fourfold, meaning that hyper-efficient star formation wouldn't be necessary to achieve the same results. In any case, in opposition to the 13.7 billion years found from alternative information, early dark energy models maintain that the universe is only 13 billion years old. A second conceivable explanation is that astronomers have erroneously identified stars as the source of part of the universe's light. The light likely comes from gradual accretion disks around really massive black holes, as indicated by Bond-Culin, who thinks this is the most probable explanation. Having only seen a small number of these galaxies thus far, astronomers caution that the small sample size probably won't be demonstrative of the whole universe. The pressure that was noted could disappear if careful statistical studies were conducted by Penn State professor Joel Rykowski, who had no contribution to the study. However, is it true that these galaxies are extremely far away? Nearby low-mass galaxies can seem like far-off massive ones, as called attention to by Peter Bauru of the University of Arizona, who is also not associated with Bond-Culin's study. Extra measurements are required to arrive at authoritative resolutions. Most critically, spectroscopic perceptions of these galaxies are still absent, which would permit us to gain proficiency with their genuine distances and search for proof of black holes. Considering new data, Michael Bond-Culin predicts that the reality of the matter will become clear in a few years, if not sooner. We can check the cosmologists out speculations on this event. To pass the time until we get this data, and at this point unidentified interaction might work. Here, as per a few stargazers, if we expect that gigantic dark openings may have existed in the early universe, then this question could be tackled. Taking everything into account, if this supposition is right, we will eventually figure out the presence of huge worlds in telescope studies. The test, however, is to give an explanation for the abrupt expansion of dark openings in the early universe. This is where an exceptionally quarrelsome theory put out by a Nobel laureate comes into play, an attack on credulity. According to the currently accepted record of creation, about 14 billion years ago, all that is or ever will be existed within a small, perpetually thick point. Everything in our noticeable universe started from this peculiarity, which emitted the Big Bang. While this concept can be summarized to this degree of simplicity, still a lot of physicists imagine that 13.7 billion years is not long enough for complex designs, like superclusters, to develop. The standard Big Bang hypothesis is being tested by an Oxford University researcher who desires to make his statements using the remnant of the cosmic microwave background radiation, which was created when the universe was just 300,000 years old. As indicated by this researcher, the Big Bang was only one event in a long series of similar blasts called ages, rather than the beginning of time. Another epoch in astronomical history was marked by all of these events. Roger Penrose, who was awarded the Nobel Prize in Physics in 2020 for his work on dark openings and mathematical approaches, has proposed the theory that our universe has seen many Big Bangs and that there will be another in the future. The development of mathematical techniques that Penrose helped advance led to the Nobel Prize in Physics. These techniques approved and developed Albert Einstein's general theory of relativity. Regarding dark openings, he investigated their complexities and showed how thick objects break down under gravity to form singularities or spots of boundless mass. Penrose reiterated his capricious thought, calling it insane while accepting the award. As the universe continues to expand, eventually all matter will break down, setting off another Big Bang and the start of an entirely new universe. In an interview, Penrose shared his firm conviction that the Big Bang was not the beginning but rather that there was something before it and that something else is not too far off for humanity. So, how does the researcher back up his theory, which he calls conformal cyclic cosmology? 6 problem areas overhead, called peddling points, each around 8 times greater than the width of the Moon, have been viewed. According to Sir Roger Penrose, who is testing the current Big Bang hypothesis, these points, which are named after the late Professor Stephen Hawking, who hypothesized that dark openings dissipate in the wake of producing radiation, demonstrate the possibility of their presence. However, it is highly improbable they could be seen within the current age of the universe, which is 13.77 billion years. Penrose states that our universe is neither the first nor the last, but rather that it evolved from a densely packed, highly organized mass into the complex reality that we see. Unless something happened long before the Big Bang, the current expansion-based Big Bang model cannot account for the presence of a low-entropy, highly ordered state during the birth of the universe. Our universe has and will again return to a low-entropy state as it moves toward its final evolution into nothingness, abandoning a cold, dark, featureless void. According to Penrose's hypothesis, dead dark openings should be visible. They are the remnants of universes or epochs that have passed. An affirmation of this could also lend credibility to Hawking's hypothesis. A monthly notification from the Royal Astronomical Society covered Penrose's 2020 paper, where he found evidence of hot, round irregularities in the microwave background. The data on these sites were validated by around 10,000 simulations and came from the Planck's 70 GHz satellite. Penrose suggested in 2018 that radiation hotspots in the cosmic microwave background could be the result of dark openings disintegrating. According to a cyclic cosmology paper by Penrose and Veith-Gardan in 2010, the uniform temperature rings in the cosmic microwave background, CMB, are the result of gravitational wave marks from dark opening crashes in a previous universe. Entropy is reduced since dark openings emit radiation and obliterate matter. The last dark openings will either disappear or combine as the universe approaches the end of its evolution, bringing back some semblance of order. This smooths out the spacetime calculation from its current battered shape and results in a state like the Big Bang. After the universe stops expanding, Penrose's model predicts that it will break down into a highly organized system, marking the start of another epoch that will culminate in the next Big Bang. In opposition to mainstream thinking, Penrose argues that variations in CMB temperature should not be random. Evidence of gravitational waves from ages past was suggested by more than 12 concentric rings that he and Gardan found in NASA's WMAP satellite data. If confirmed, Penrose's conformal cyclic cosmology would imply that our universe is just one among many potentially vast ages, thereby precluding the need for a singular Big Bang. However, this idea presents serious challenges to long-held beliefs in the cosmology community, and if proven correct, it would have broad implications. Certain individuals find it hard to believe that the universe can go from being infinitely large one moment to being incredibly tiny the next, implying that particles would have to lose mass as the universe becomes older. Share your thoughts on whether Penrose's hypothesis holds water or if it's another Big Bang idea that will fade into obscurity. For more, subscribe and leave a like.